Okay.
in the discussion. So next speaker is Renjan R from IIT Pune, and he'll speak about anyonic correlation functions in Chern-Simons series. So 13 minutes plus 2 minutes for questions.
Okay, thanks. Can you see the screen?
Yes, yes.
Okay, so the title of my talk is Anyonic Correlation Functions in Chern-Simons Matter Theories. This is based on a work done with Yatharth Gandhi, who was then a BSMS student, and Sachin Jain from IIT Pune. So in a three-dimensional CFT, it has been shown that a generic three-point spinning correlator has three structures, two of which are parity even and one parity odd. For example, in the case of the three-point function of stress tensor, one gets a parity even contribution from free boson, another parity even from free fermion, and a parity odd contribution which doesn't come from any free theory. So while now the parity odd structure contains the Lepie-Civita tensor, and there is no apparent relation between the three structures that contribute to the correlation function. In this talk, what we would show is that the entire three-point CFT correlator can be obtained from just the free bosonic or the free fermionic theory. We will then apply this in the context of Chern-Simons matter theories, and there we'll see that the full three-point function can be obtained from the same correlator in the free theory after an appropriate multiplication by an anyonic phase factor that depends on the coupling. Before we go into the details, we'll first discuss the important ingredients that go into our analysis. So we begin with a discussion on two-point functions, which should hopefully set the stage for three-point functions. Let us begin by considering the two-point function of the conserved spin 1 current, denoted J. The even part of the correlator is given by a the transverse projector times the momentum, magnitude of the momentum, and the odd part of the correlator is given by the epsilon Lepie-Civita tensor contacted with the momentum. Now, given these expressions, one can easily check that the following relation holds between the odd and the even parts of the JJ two-point function. Similar relations hold for TT two-point functions also. And if your theory has higher spin currents, then such a relation between the odd and even parts continue to hold even for the two-point function of higher spin currents. In our analysis, we make use of spinor-helicity variables, in terms of which the relation between the even and odd contributions to a correlator becomes manifest. So let us have a very quick review of these variables. We write momenta in terms of SL2C spinors lambda and lambda bar, and they're related to the momentum through such a relation. And here epsilon is an antisymmetric 2x2 matrix, which defines the spinor brackets, which are the dot inner products between your spinors. Now a spinning operator has two helicities, which we denote by plus and minus. And when the tensor indices of the operator in momentum space are contacted with polarization vectors, the operator gets projected along one of the two helicities, and we denote them by J plus or J minus. Now in spinor-helicity variables, the two-point function has a unique structure, and the even and odd correlators differ only by a factor of I. For example, for the spin 1 current, the even and the odd parts of the two-point function are given by this bracket here. And notice this factor of I here. So the entire two-point function, which is like a C1 even plus C2 odd, is given by such an expression. Now, the other non-zero helicity component of this correlator is the J plus can be obtained by a simple complex conjugation of this result. Now let's look at two-point functions in the particular theory of Chern-Simons matter theories. So these are fermionic and bosonic theories coupled to the Chern-Simons gauge field. And the two-point functions in these theories have been computed in this reference marked in red. And they were reported to be this. If you convert this into spinor-helicity variables, it takes the form which is given here. Thus, we see that in spinor-helicity variables, the two-point function in the interacting theory is given by the two-point function in the free theory, dressed with an appropriate anyonic phase factor. Now, this is for the spin 1 case. It can be seen that this generalizes to our two-point functions of arbitrary spinous currents. Now that we have discussed two-point functions, let's come to three-point functions. Here we need to introduce the idea of homogeneous and non-homogeneous contributions to a 3-point correlator. So in a 3D CFD, we can split a correlator into its homogeneous and non-homogeneous pieces, as shown here. And this comes from the action of the generator of special conformal transformations in Spinor-Helicity variables. So if you take your generator in Spinor-Helicity variables and act on a correlator, it is not zero, but what it gives is terms from the 𝗦𝗀𝗀𝗀𝗀𝗀 identity for the correlator. And the homogeneous part is, as the name suggests, is the part that is killed by the generator, and the rest of it, which contributes to the 𝗦𝗀𝗀𝗀𝗀𝗀 identity, is the non-homogeneous contribution. In the DS4 language, this corresponds to, the homogeneous space corresponds to, say, the Einstein gravity, and the non-homogeneous space corresponds to the W-cube contribution. Now, one can check that a 3-point correlator satisfies the same 𝗦𝗀𝗀𝗀𝗀𝗀 identity in the free boson and free fermion theories. This implies that their non-homogeneous contributions are the same, since the non-homogeneous contributions are given by the 𝗦𝗀𝗀𝗀𝗀 identities. Now, the homogeneous contribution is uniquely determined up to a theory-dependent coefficient for a given correlator. Now, if we combine the second and if we combine the above 3 bullet points, we can write the 3-point correlator of the stress tensor in the free boson and free fermion theories as the sum and difference of the same non-homogeneous and homogeneous pieces, as we have shown here. And this has also been checked by an explicit computation of these correlators in the free theory. Now we make use of these expressions for free boson and free fermion in terms of homogeneous and non-homogeneous to write the 3-point correlator in a generic CFD as in the last line. Now what we can do is, as was mentioned, the relation between the parity even and the parity odd parts of a correlator are made manifest in the Spinor-Helicity variables. So you go to Spinor-Helicity variables and express the odd part in terms of the even part, the homogeneous part of the even correlator, and the relation takes this form. This helps us re-express the TTT correlation function as the sum of non-homogeneous piece and the homogeneous piece, as a weighted sum of the non-homogeneous and homogeneous piece, and the homogeneous piece gets this phase factor times the gamma t. So we emphasize that the homogeneous and non-homogeneous pieces come from the free theories, and hence effectively we have been able to write this correlator purely in terms of the free theory. Now that we have discussed 3-point functions in a generic CFD, we'll focus on 3-point functions in Chern-Simons theories. So in these theories, once you have given in the known values of NB, NF, and N0 from the literature, the 3-point function TTT in the Chern-Simons theory takes this form. So here I have written it for the fermion coupled to Chern-Simons gauge field, and lambda f is the coupling. So what we see is the homogeneous piece gets the anyonic phase, and this interpolates nicely between the lambda f goes to 0 theory limit and the lambda f goes to 1 theory limit. So as you can see, as I have illustrated in the picture, when you take lambda f goes to 0, the correlator gives you non-homogeneous minus homogeneous, which was how you had originally had your free fermion correlator. And when you turn on lambda f, it gets it comes out of here, and once you take lambda f all the way to 1, you get the correlator to be non-homogeneous plus homogeneous, which is the free boson result that we had started with. Interestingly, it is the same anyonic phase that appears in the all loop 2-to-2 scattering amplitude in Chern-Simons matter theories that appeared in this paper marked in red. Now this analysis that we had for the 3-point function of stress tensor directly extends to the 3-point correlators of any spinning operator, and the result takes the form as shown here. Okay, so to conclude, we made use of Spinor-Helicity variables which make manifest the relation between parity even and parity odd parts of a CFT correlator. We use the fact that the correlator can be split into homogeneous and non-homogeneous contributions. And these two factors helped us express 3-point correlators in a generic CFT purely in terms of the free boson or the free fermion correlators. And in the context of Chern-Simons matter theories, these took an interesting form where the correlator is given purely by the free boson or the free fermion correlator appropriately multiplied by a phase factor, which nicely interpolates between the free fermion and the free boson limit. It would be interesting to see if the anyonic structure extends to 4-point functions. And another question we can ask is, can we have anyonic currents whose correlation functions we can compute just as in the free theory? Thank you.
Okay, so we have time for a few questions. So I guess Sunil Mukhi has a question.
Yeah, just a very naive question, since I'm not quite, I don't know the results in detail, but it seems like you have a general result that Chern-Simons, is it a result for general Chern-Simons theories that correlators can be expressed in this form in terms of free boson and free fermion correlators?
Yes, it is.
Okay, and does that suggest that they might have a map to some free theory?
Yes, I mean, I don't think it is known yet, but it will be a good thing to have a free field realization of these theories. Yes.
Okay. One reason I ask is that, generic �𝗏𝗏𝗧 models. So for level 1, we know that 𝗏𝗏𝗧 models on simply laced groups are free theories, and we know the map. But for higher levels, beyond 1, 2, and 3 or so, it's generally not the case as far as I know. So I wonder whether this tells us something new about 𝗏𝗏𝗧 models. That would be quite remarkable.
Okay.
Anyway, leave it there. Yeah, thanks.
Okay, so next Shiraz has a question.
Hi. As you know, there are these the spin S currents obey the kind of equation del J is equal to JJ in general.
Yes.
Plus JJJ. So let's forget about the 3J terms. Do the expressions that you have here, do they take into account the JJ part as well, or is it only for those 3-point functions for which the JJs don't contribute?
This is for all. So this, what I know is this applies for all 3-point correlators where the triangle inequality is satisfied, even if the currents are weakly broken.
And are there 3-point functions where the triangle inequality is not satisfied?
Yes, and there are, if you write J4, JJ.
Okay, and so your expression does not apply to that case?
No, sorry, it applies, Renjan. It applies, sorry.
So it applies to every case, including the contribution of that JJ.
Yeah, it's just the distinction between non-homogeneous and homogeneous does not exist outside the triangle. Every correlator becomes non-homogeneous outside the triangle. And you can actually write this non-homogeneous, one of the non-homogeneous free boson plus free fermion, and other non-homogeneous has free boson minus free fermion. You can also identify them just from the free bosonic theory. So this relation is generic.
So for all currents.
Yeah, for all currents, yes.
Thank you.
In fact, you can actually derive the non-conservation, what you pointed out, just starting from the free theory 𝗏𝗏𝗀𝗏𝗧 identity by doing some transformation.
So does this suggest that if you redo 𝗦𝗏𝗀-𝗪𝗏𝗃 in spinor helicity variables, the analysis would be much simpler?
So 𝗦𝗏𝗀-𝗪𝗏𝗃 analysis just becomes trivial with the identification. So Renjan has not shown a identification in the momentum space between parity even and parity odd. With that, it becomes trivial. The equations directly, 𝗦𝗏𝗀-𝗪𝗏𝗃 equation directly maps to the free theory equation, and that becomes trivial.
Okay, thank you.
Actually, we have been able to actually do it for the 4-point function as well. So the full 4-point function just directly maps to the free theory higher spin equations also.
Thanks, Achal.
Look, we have 1 minute for a question.
Yeah, just a small question, Renjan. Hi. So is there if you look at the full TTT correlator in the Chern-Simons theory, I mean, is there a double copy relation for that? I mean, not in just in the free limit. I mean, can you write it from the square of the current correlator?
Yes, that can be done. Yes, and
for the exact thing, the whole thing, TTT.
Yes, it has been done. Yes.
I see. And what is the, I see. So it's the, in the same theory, you look at the JJ correlator and you do a double copy and you get this TTT.
Yes. Right. Yeah.
Okay. Thanks.